In this video, we solve problems 15.5.009 and 15.5.012.mi from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the rectangular equation for the surface by eliminating the parameters from the vector valued function. And we've got one vector valued function for problem 9 here, and then another one for problem 12. Then we're asked to identify the type of surface and sketch its graph. Now, these first, well, actually for all of these parts, these are the types of questions that I might ask you to do on a paper-based exam over this material. It's a little bit harder to do in WebAssign, so we'll talk about how you might choose the appropriate surface after doing all of your work on paper. But let's do that work on paper first. And I'd also like to switch from this form in terms of the standard unit vectors I hat, j hat, and k hat to component form, which I think is a little cleaner. Our x component is u, our y component is v, and our z component is v over 2 for that surface. And then for this surface, our x component is 3 cosine of v cosine of u. Our y component is 3 cosine of v sine of u, and our z component is 5 sine of v. Okay, so we'll just do one surface at a time. We'll start with that first one first. Now, if I want to come up with the rectangular equation for that surface, that just means I want an equation that does not have a u or a v in it that relates x, y, and z to each other. That would be the rectangular equation for that surface. So we'll start here writing this down. Then we'll identify x of u and v and y of u and v and z of u and v. We'll drop that dependence on u and v. So we'll just say x equals u, y equals v, and z is equal to v divided by 2. And then we'll usually substitute to get rid of the variables. Now I see here that y is equal to v and z is equal to v over 2. I can replace this v with y, and that will get me the equation of the surface. So v is equal to y, so I'll plug that in for v here. So I have z is equal to y over 2. And that doesn't say anything about x at all, and it doesn't say anything about u. So that would imply that x is free to be anything, and we're just on the surface that is given by this equation. Now, typically, we would see the equation in this way. Let's multiply both sides by 2. And let's subtract that y from both sides, or subtract the 2z from both sides. Let's do that instead. And we see we have a plane. And when y and z are 0, that we get 0. So that satisfies the equation of the plane. And there is no x in this, so x is free to be anything. So that means our graph is going to look like this back in the YZ plane. If you want, you can think of z as a function of y. So z is 1/2 of y. When z is 0, y is 0. And we would go up 1 and over 2 to find another point on that line. And then do it again, up 1 and over 2. And just draw a line through those points. It kind of looks like that. Should be straight, but it's not. Now x is free to be anything. So we can imagine this line is just sort of coming out of the page. If this is our y-axis and this is our x-axis, our y-axis and our z-axis, our x-axis should be coming straight out at it. It's like my thumb or like my pen here. The x-axis would look like that. And since x is free to be anything, we would see that plane coming out of the page at us. I like to demonstrate this with this stack of sticky notes. So the plane would look something like that coming out of the page at us. Now it's hard to draw with some dimension. We'll try. There's the z-axis, there's the y-axis, and we see this plane looks like this. But we want to imagine we're looking at that from some angle, and it's really hard to imagine. So I think I'll just draw it like that. Sort of x is free to be anything. So I'm imagining taking that line given by z equals 1/2 y and moving it forward and backward. It's not the best plane I've ever drawn, but I hope that you get the idea a little bit. But that line right there is intended to be z equals 1/2 of y. Okay, and x is free to be anything, shouldn't have any x component, should just be coming straight out at us. And the way I've drawn it, it looks like it's going down. It's not supposed to be going down at all. It's supposed to be coming straight out at us. So we do the best we can. Now, these are the options in WebAssign, which are difficult to choose from. The answer is this first one here. If you're saying, how do I know that is the plane that I'm looking for as opposed to these other 3 planes? What I would suggest is that we are looking for a plane that when you look at it from this perspective, where x is going to the left and y is going to the right, the plane is supposed to look like this if we look at it from the x-axis straight on. So it's going to look just like that. If I looked at it from a different angle, so that my x-axis was sort of pointing like in a perpendicular, well, it's always pointing in a perpendicular direction. But if I looked at it from a different angle, that plane should be sort of sloping up in the y direction. And this is the only plane, well, this plane and the second plane here are the only ones that sort of slope up in the y direction. But we also have to imagine that our x is free to be anything. So we're just seeing this line moved forward and backwards. So I shouldn't see that plane sort of going down in the x direction at all, or, you know, there should be sort of no fluctuation in the x direction. I should just see that line. And this one looks like it's sort of pointing down in the x direction relative to us. This one looks like I would see approximately the same line. So that's how I would infer that. I know you guys have 100 chances to guess on this one. So you'll definitely get this right if you do this, you know, more than 4 times and choose all the options. But that's how I would decide among those 4 graphs that are given to you on WebAssign. Okay, so we're asked to find the rectangular equation for the surface. And we did. And I tried to draw it, but unsuccessfully made it look like it was going down in the x direction when it's not. That is our rectangular equation. And the next question asks us to identify the type of surface. That's a plane. And then we tried to sketch its graph. That was the best I could do. Yeah, but you just choose from among the graphs on WebAssign. If you're drawing a plane in our class, usually we just draw the first octave portion of that plane. If it's something like this one, just do the best you can, and that would be totally fine with me. Now, for the second surface, we've got x equals 3 cosine of v cosine of u. Y is equal to 3 cosine of v sine of u. And z is equal to 5 sine of v. We had this times I hat plus this times j hat plus this times k hat. I'll drop the dependence on u and v. Notice that we've got a lot of trig functions. That tells me I'm going to be using that Pythagorean identity. I've got cosine of v here and here and a sine of v there. Oops, that should be a cosine of v. And I've got sine of u here and cosine of u there. And we want to eliminate those two parameters, u and v. We'll just eliminate them one at a time. Remember that cosine or sine squared of an angle plus cosine squared of the same angle is equal to 1. This time I'll use my angle u. So I will take this equation and solve for cosine of u. Cosine of u, if I get it by itself, turns out to be x divided by 3 times cosine of v. So I'm just dividing both sides by that to get cosine of u by itself. Similarly, if I want to solve this for sine of u and it's multiplied by 3 times cosine of v, I will divide both sides by cosine of v, 3 cosine of v, and we'll substitute those into this equation. So we've got sine squared plus cosine squared equals 1. And sine of u is y over 3 cosine of v. And cosine of u is equal to x over 3 cosine of v. So we've got two fractions here, square the numerator, square the denominator. Here you've got a product, square each factor separately. 3 squared is 9. We have cosine squared v. Similarly, 3 squared is 9, and we have cosine squared v there, equals 1. And then if I want to get rid of these fractions, I notice that I've got a 9 cosine squared v in both denominators. Let's multiply both sides by that 9 cosine squared v. When we do, these fractions will clear, and we'll have a 9 cosine squared v on this side. Okay, so we know that is true. And we also know that z is equal to 5 sine of v. Well, there's a sine of v there and a cosine squared v there. So we can solve for sine of v, then square it, then we'll have sine squared of v, and then we'll be able to solve this for cosine squared v, and we know that sine squared of v plus cosine squared of v should equal 1. So let's take this one and first solve for cosine squared v. Cosine squared v is y squared plus x squared divided by 9. If you want, you could divide each of those terms by 9. It's up to you. You don't have to, but you can. And then here, if I take this equation for z and solve for sine of v, I get this. Z divided by 5, because I'm dividing both sides to get sine of v by itself, is equal to sine of v. Now, if I square that, I get z squared over 25. Okay, now we know cosine or sine squared v plus cosine squared v is 1. Let's substitute those in. Sine squared v turns out to be z squared over 25. Cosine squared v turned out to be x squared over 9 plus y squared over 9. That's all set equal to 1. Let's write it in a more traditional order with our x first, and then our y, and then our z. Well, that's the equation of an ellipsoid. That was the second question. Identify the type of surface. This is centered at 0, 0, 0. We can tell because x naught, y naught, and z naught, those are the coordinates of our center, are the numbers that we're subtracting from x, y, and z, and we're not subtracting anything from those. And then these numbers that are squared in the denominator, they tell us how far to go in the x, y, and z directions from that center. So typically we would say this is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And we can use that to graph this. So I noticed that my a squared, that's the number under the x squared, is equal to 9. So take the square root. A is 3. So that means we're going to go plus and minus 3 units in the x direction from the center, which was 0, 0, 0. So those are points on our ellipsoid. B squared is also equal to 9. So b is the square root of 9, or 3. That's under our y. So we're going to go plus and minus 3 units in the y direction. So we end up with a circle of radius 3 in the xy plane. And then c squared, that's the number under z, is 25. So c is 5. That means we're going to go plus and minus 5 units in the z direction. And we get this. Kind of reminds me of a peanut M&M. Alrighty. So we've got an ellipsoid centered at 0, 0, 0, and these numbers tell us how far to go in the x, y, and z directions. And the rectangular equation of the surface can be written this way, but I prefer it in this form because it looks more like the standard form, that equation of an ellipsoid centered at 0, 0, 0. Let's go to the homework. A web assignment is expecting an answer that looks like this. I, of course, prefer this form because it makes it more obvious how many units to go in the x, y, and z directions. It's an ellipsoid. And then when you sketch its graph, if I was sketching the graph on an exam, I would do it just like we did on this paper. But here I just have to look for the surface that looks right. That's a sphere, so that's not going to work. But this one will. Notice that we are going plus or minus 3 units in the x direction. And it's a little harder to tell that it's going plus and minus 3 units in the y direction. But we do see that the z values are going from -5 to 5. So I would say, yes, that's my surface. We would select that one. Of course, when you're doing WebAssign homework, you just do the best you can and you've got lots of options. But remember, we're preparing to graph all of this by hand. So make sure that you are comfortable coming up with this graph yourself rather than selecting a graph from your 4 choices.